Hey guys, Rao this side. Welcome to GATE Conqueror channel. By end of this discussion, you are going to get clarity on three things. First thing is design of insulation. What is the main design constraint in the design of insulation of machines or whatever it may be? Voltage. What is the main design constraint in the design of conductor, copper conductor and all is going to be current. For the conductor, it is going to be current. For insulation, it is going to be voltage. Most of the members know. But in the design of insulation, that particular voltage, is it peak value of voltage or RMS of voltage or average of voltage? We'll come to know by end of this discussion, one thing. And second thing is it possible to create black hole? Yes, black hole in capacitance. Second thing. And third thing is Coulomb's law. Coulomb's law. Can we apply Coulomb's law to the electric dipole also? You are going to get the clarity. Anyway, before starting our discussion, let me share a few details of myself. I'm Rao. I completed 20 years of GATE training by GATE 2021, GATE ESE training, and I worked in very good organizations only. Okay, and subjects electrical machines, network theory. I may plan to take power systems also. Okay, and if you want me motivated towards doing this kind of sessions in YouTube, okay, because we are really working hard. So you can like this channel or like this video, subscribe to the channel, share to your friends. And if you want me to be part of your preparation, use this code while purchasing your subscription. Okay, such that you will get 10% of the discount. Any code you are going to get 10% of discount, but you will get my personal assistance obviously. And here there are two kinds of paid platforms in Unacademy. One is Plus and another one is Iconic. In Plus, you are going to get live classes, crash courses, weekly tests, doubt solving, rank improvement batches, and you can attend the classes either in English or Hindi. And if you think this is basically subject, and beyond that, if you want beyond this assistance, kind of personal coach, okay, personally he can tell you he should be an achiever of your age band, such that he'll be able to understand your problems properly, and he can guide you properly. And study planner, okay, especially this will be useful for working guys. And the study booster sessions will be there, personalized test analysis will be there, and kind of materials also they are going to provide. This is going to be Iconic subscription. Now, if you see for Plus subscription, if you use my code KNR10, you can get it for 27,225 for 12 months, and for 18 months, 1.5 year, this is going to be 34,650, and for 2 years, it is going to be 39,600. And if you think of Plus subscription, for Plus subscription for 1 year, Iconic subscription, for Iconic subscription for 1 year, it is going to be 40,500, and for 2 years, it is going to be 54,000. And they thought of increasing this fees from July 1st onwards, but they didn't because of huge demand from the students. But definitely they are going to increase very soon. So if you want to subscribe soon. And here there are two kinds of batches. One is Lakshya batch and another one is Arohan batch. Lakshya batch is meant for GATE ESE 2022 and Arohan batch is meant for GATE ESE 2023. Okay, and obviously as of now in Unacademy, top faculties, India's top faculties are working with Unacademy only. And kind of Ankit Goel, Aditya Kanwal, Suresh sir, Bhimashankar sir, Vishnu sir, Varun Srivastav sir, B.V. Reddy sir. And with most of them I worked in my previous organizations and all. They are all obviously top faculties. Now if you think of ECE, for electronics and communication, for that department also same thing. Lakshya batch will be there, Arohan batch will be there, and again top faculties are there. Okay. Now if you think of test series, they are providing some free test series also, and obviously for paid platform, you are going to get more test series. Okay. And here this upcoming scholarship, okay, combat. Every Sunday, Unacademy is going to conduct combat, but this Sunday it is very huge because 4 crores scholarship is there, and the top 3 rankers are going to get free 1 year subscription, and remaining 4 to 10 are going to get 75% scholarship, and all they are going to provide some scholarships also for the toppers, and also for 500 lucky participants are going to get iPads kind of. Now, if you want to follow me in Unacademy app, follow me here, Rao for you, number 4U, such that you will be getting the notification whenever I come to take special classes or whenever I come to take Plus classes and all. Now, In this session, our main discussion is going to happen on capacitance, right? So let me think of. It is capacitance, meaning that ideal property. It is not practical property. Okay. Now, see here, in any material, any atom. If you think of atom, nucleus, positive charges will be there, and my electrons are going to be revolving around it. Okay. Now, my point of interest is not electron. Okay, but center of gravity of electron. And one more thing is, in while discussing Ohm's law, Ohm's law is defined only for conductors. What is electrical conductor? Those valence electrons, whatever you do, those valence electrons are ready to come out. But if you think of insulation, from insulation, this particular any electron, no electron will come out. Whatever you do, okay, you may heat it, or you may supply light energy, or you may supply electrical field. Whatever you do, those valence electrons should not come out. That is the property of insulation. Okay, now see here, if I see center of gravity of positive charge, obviously we will be lying at the center. Okay, because of all these revolutions of all these electrons under isolated stable condition, it is going to be lying there. Let me take one example, kind of hydrogen, which is having only one electron. Then you will understand. Okay, now if I have kind of only one electron, then easily we can connect. Now that electron should revolve like this, or should revolve like this, such that center of gravity of electron should lie at the center only. Okay, now let me think of, for example, rather than like this, under isolated stable condition. Now, for example, if one electron is revolving like this, one electron is revolving like this, under that condition, where that negative center of gravity will lie, at the center of this. Okay, then there will be huge attraction force. Between these two. Anyway, atom is under isolated conditions only. Then what will happen? This particular orbit will slide towards left, such that my negative center of gravity will lie to here only by moving the slide, by sliding that particular orbit towards left side. Okay. Now, are you convinced now that positive center of gravity and negative center of gravity are going to lie at the same point under isolated stable conditions? Our main focus is center of gravity. Okay. Now let us think of capacitance. What is capacitance? Two conducting plates separated by insulation is nothing but capacitance. So let me think of one capacitance like this. This is capacitance. Okay, inside insulation is there, no? That insulation, positive center of gravity and negative center of gravity will lie at the same point, and at the same time no electron will come out. Okay, now if I think of positive center of gravity is here, negative center of gravity also will lie at the same point. Okay, and without applying any voltage and all. Now if I have the same capacitance, and if I apply positive negative voltage here, then what is going to happen? This positive will be repelled by this, positive will be attracted by this, and negative will be repelled by this, and negative will be attracted by this. At the same time, can electron break down that bond, and can they come out? No, it's an insulation. So positive is going to slide down and negative is going to go up. But again, electron cannot come out. This is electric dipole. Okay, kind of, let me tell you. For example, one atom is there like this, for which our electron is revolving like this. Okay, now if I maintain huge charge here, then what will happen? My electron will be attracted towards this. Okay, my electron flow will be against to the direction of electric field intensity. So if I think of electric field intensity in this direction, my electron will be attracted in this direction. Such that at the same time, like conductor, electrical conductor, in the sense these valence electrons will come out and accelerate, but can valence electrons come out in insulation. No, it cannot come out. So the moment it cannot come out, it is going to slide like this. Okay, my orbit is going to be slided towards this, Then what will happen? Negative center of gravity is going to be here. Negative center of gravity for this is going to be here. Positive center of gravity will be here, such that dipole, electric dipole is going to be formed. Okay, now see here. Now for the same capacitance, if I apply more voltage, okay, then what is going to happen? Again, the dipole distance is going to be increased. Okay, distance of the dipole is going to be increased such that negative will become here, positive will become here, and again bonding will be there. Okay, slowly we are going to understand. We need not rush into the things, because directly if you apply formulas and all, then many doubts will come, especially in the application oriented subjects. Okay, now let us think of same capacitance. Let me reduce voltage. To this level. Then what will happen? Same kind of setup will be there to here. Okay. Now let me think of, if I reduce the voltage to 0 for the same capacitance, these two are conducting plates, in between insulation is there, and I'm considering only one atom for the explanation part. Okay. Now then what is going to happen? Means if I don't apply any voltage, if I have plus here, minus also will be lying on that only. Now, see here, there are many conclusions we can bring. Okay, see here, why this particular electron is unable to come out? Though means segregation force is there in this direction. Let me use black. Segregation force is there in this direction. Okay, so this positive is being attracted toward this. And one more thing is mobility I'm not considering. I'm considering that for positive and negative, mobility is equal. That's why distance I have shown equal. Otherwise, normally we know electron mobility is more, right? So the moment electron mobility is more, then what is going to happen? Means positive will be slided slightly, but negative will be slided more, if I consider mobility into account. Okay, but for time being, I'm not considering mobility into account at all. No. Anyway, these two, electric field is trying to segregate that particular charges, but there is a strong attraction force. Between these two, such that whenever this attraction force equal to the segregation force, then stable point will come. Okay. Now here also, if you see, there is a attraction force between these two, and there is a segregation force. This is trying to segregate. Okay. So one force is trying to segregate, another force is trying to recombine. So this is going to be the stable point. If you see here also, segregating force is this, and recombining force is this, or attraction force is this. Now, let us compare this with rubber band. Okay, so rubber band, if you try to stretch the rubber band, you are trying to stretch in the segregation force, but rubber band will try to close itself, meaning that is going to be recombining force. Okay, similarly here, what is happening? Recombining force will be there, segregating force will be there. We can compare this with kind of rubber band. Okay, one thing, in stretching the rubber band, if I'm stretching the rubber band, I have to supply energy. Okay, and if I'm relieving this particular rubber band, it will supply back that energy. Right? So if I'm stretching the rubber band, you have to supply energy, and while recombining, it is going to give you back the energy. Just feel it enough. Now, similarly here also, means here we have to apply, from here to here we have to apply energy, from here to here we have to apply energy, because you are trying to stretch from here to here, stretch, you have to supply energy, and recombining, it is going to give you back the energy, such that capacitance is going to be energy storage area. Now, there are a lot of conclusions we can derive. Okay. Now, see here. If I have maybe some mass, okay, so let me think of, this is my mass. Okay, this particular mass, can I change the position of this mass from here to here instantaneously? Getting my point, right? So, can I change the mass of this particular phone? Can I change the position of this particular mass from here to here instantaneously? No, we cannot change. Why? Because if I am able to change the position of this mass from here to here instantaneously, meaning that at that instant, how much should be the velocity of that particular mass? Should be infinite. But by theory of relativity, nothing can go beyond light velocity. Nothing can go beyond light velocity, because if anything is gaining light velocity of light, meaning that it will lose its mass properties and it is going to gain wave properties. Wave properties. So, point here is no mass quantity can change its position from one position to another position instantaneously. It's an impossible task. If you are able to do that, it will gain huge gravitational force such that you are going to create a black hole. You are going to create a black hole, right? Now, these charges also, center of gravity of charges, are electron. Is it going to have some kind of mass or not? Yes. So, the orbit of the electron, can I change from here to here instantaneously? No. If I am able to do it instantaneously, meaning that inside capacitance, you can create black hole. You can create black hole, isn't that? So, means these are associated with masses. So, the moment if you are able to move from here to here instantaneously, here to here instantaneously, here to here instantaneously, or here to here instantaneously, meaning that indirectly you can create black hole inside the capacitance such that our complete earth will sink into your capacitance. Okay? Is it possible? No. 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 See here. Here, I am applying 0 volts. Okay. For example, let me assume that from compared to 0 volts, it is increased to 5 volts. Segregation force. And from here to here, I increase it to 10 volts. From here to here, I reduce to 5 volts. From here to here, I reduce to 0 volts. 0 volts. Okay. Now, means from this position to this position, I cannot change instantaneously. What does it mean? Can I change from this position to this position instantaneously? No. No. If you are able to change voltage across capacitance instantaneously, meaning that you are creating black hole. You are creating black hole. Is it possible to create black hole? No, not possible. Not possible. So, instantaneous voltage change is impossible in a capacitance. Instantaneous voltage change is impossible in a capacitance. Of course, mathematically, we may have some kind of questions like, let me tell you, maybe this particular question you may find in some books. Okay, if it is charged to 10 volts, if it is charged to 8 volts, if I close the switch, instantaneously, voltages are going to be changed, but that is on paper. On paper, your wish, because it's your paper, it's your pen. Okay, so you can change anything. On paper, I can move from here to here instantaneously, but that is paper, that's your paper, your pen. But practice will not accept that. Practical scenario of electrical systems will not accept that. Okay, now anyway, let us come back. Okay, this is the situation. So, conclusion is very simple. From here to here, instantaneously, we cannot change the positions of the masses, meaning that instantaneously, I cannot change the voltage across capacitance at all. So, you please make a note of that. Instantaneous voltage change across capacitance is impossible. Make a note. Now, coming to the point, instantaneously, I cannot change, but after taking some time, I can change. So, while having the change, I repeat, while means while increasing the voltage from 0 volts to 5 volts, while instantaneously anyway we cannot. So, while having that, this positive is coming down, meaning that current is in downward direction, positive is coming down, and the negative is going up, meaning that positive current is also coming down, because negative is going up, meaning that positive current is coming down. Okay. Now, while moving from here to here, positive is going down. Positive is going down, so direction of current is in this direction. Negative is going up, meaning that current will be in the same direction. While moving from 5 to 10, we cannot move from 5 to 10 instantaneously. Now, while moving from here to here, positive is going up, so positive current should be in upward direction, and the negative is coming down, so current is in upward direction. While from here to here also positive is going up and negative is coming down, so current is in upward direction. Now, see here, whenever I am moving from 0 to 10, what is happening? Current is in downward direction. 0 to 10, current is in downward direction. And 10 to 0, while moving from 10 to 0, current is in upward direction. Okay. What about the polarities of voltage? From here to here, polarities of voltage is same. Okay. Always upper one is positive, and lower one is negative. Getting my point, right? So upper one is positive, lower one is negative. Lower one is negative. So point here is from, what do you say? Let me think of from here to here. Always upper one is positive. Current is entering into this. Let me think of this as IC. Voltage across this is VC. And from here to here, if I analyze, voltage is upper one is positive only. A voltage, but current is coming out. Now, can we connect this passive sign convention or not to the passive sign convention or not? Yes, we can connect, because current is entering into positive terminal voltage, meaning that particular element should absorb power, should absorb energy if you multiply with time. Okay, so because power is nothing but rate of energy, you know. Now, current is entering into positive terminal of the voltage. You have to supply energy, and the current is coming out of positive terminal. It is going to deliver energy. That's what we discussed, you know. Okay, see here, from here to here, you are stretching the rubber band. Here to here, you are stretching the rubber band. You have to supply energy. From here to here, you are relieving the rubber band. So, it will deliver energy. So, passive sign convention is matched. Now, coming to the other point. Now, let us think of okay. Now, let us see breakdown voltage. Okay. About breakdown voltage, if you see, see, let me think of capacitance here. And here, I am increasing the voltage. Voltage across capacitance, I keep on increasing. Then what is going to happen? At starting, positive, on top of that, negative will be there. After some time, positive, negative will come. After some time, if you are increasing the voltage, maybe positive, negative will come, such that distance between the dipole will keep on increasing. If you still increase, then maybe negative, positive. At one point of time, it has to break down. At one point of time, it has to break down. The moment it is broken, that process is irreversible. If it is a solid insulation, once it is broken, dielectric breakdown. So, for dielectric breakdown of insulation, definitely voltage matters. But is it maximum voltage or RMS voltage or average voltage? Okay, means see here, you are taking rubber band. Okay, so that rubber band you are stretching. At one point of time, it will break down. That means think with the mind. Okay, so that will it depend upon the average value of the force, or RMS value, or average value, or peak? This is going to be peak. That is my point, right? So dielectric breakdown. Okay, or we can write that main design constraint of insulation is it voltage now? No, maximum voltage. Now let me connect this with our machine design, for example. Okay, so I have maybe this is the insulator. Let us consider and this insulation can bear 100 volts, maximum 100 volts. Okay, at any cost you are not supposed to apply more than 100 volts. Okay, and one interview question is also there. Okay, so that interview question will be like this. Well, let me tell you that, then we'll discuss about the machine design. Okay, now if it is designed for 10 volts, okay, if capacitor is designed for 10 volts, can I apply 9 volts AC to this? Can I apply 9 volts AC to this? My capacitor, this is interview question. My capacitor is designed for 10 volts. Can I apply 9 volts AC to that? 9 volts AC to that? No. Because peak voltage should be 10 volts. But if you think of 9 volts AC, if I say, what is that 9 volts? 9 volts is going to be RMS value. So what is peak value of this? Peak value, the maximum, is going to be √2 into 9, which is more than 10. So we should not apply. Okay, we should not connect 10 volts capacitor to 9 volts AC. 9 volts AC. Because design of insulation will be decided by the peak value of voltage, not RMS value or average value. Okay. Now, let us consider machine design. Okay. In machine design, for example, you have maybe 100 volts machine or maybe 230 volts machine, just like that. Now, if you apply the insulation, if you keep the insulation of 230 volts, it will not work out because maximum voltage, root 2 into 230. Now, for example, that's why we say that design of insulation is very, very crucial compared to design of conductor. Because design of conductor, maybe later you will come to know or we will discuss when we discuss RMS value and all. Design of conductor will be decided by RMS value of current. But design of insulation will be decided by peak value of voltage. Okay. Now, for example, my machine is there for design for 230 volts. RMS. Now, if I design machine insulation for root 2 into 230, will it be sufficient? No, it will not be like that. For example, this particular machine will be used, the lifetime of this particular machine is, for example, 20 years. Okay, lifetime of this particular machine is 20 years. In 20 years, for example, at one instant of time, only at one instant of time out of 20 years, if maximum voltage is 1000 volts. Getting my point, right? So machine is there. That machine is designed for 20 years of lifespan. Normally we'll apply 230 only. But out of 20 years of life, at one instant of time, voltage can be increased to 1000 volts. Then should I design the insulation for 1000 volts or root 2 into 230? 1000 volts. Okay. Let me tell you here. For example, my sinusoidal voltage is there. Maybe because of another surge. Okay, some surge may happen. Maybe at one instant of time, this is going to be shooted like this. Just like that, for example. Okay, then our, insulation should be designed at least for that. Okay, if I think of this as voltage, if I think of this as time, okay, design of insulation should be at least for this. Now, let us think of, it is not the waveform of voltage, now it is the waveform of current. Then if you see, conductor can be designed for RMS only. Because just with one instant of time, nothing will happen to the conductor. Because, for example, this is the conductor. Okay, if I keep on increase current in this particular conductor, what is going to happen? Means my temperature of this particular conductor is going to be raised. That particular conductor temperature has to be raised till it reach melting point. Then only it will melt. It will burn. So you have time. But here time will not be there. Getting my point, right? So of course we can connect this to magnetic induction transformers. And for time being, let me leave it. Gradually we will see about this current waveform later. Now, coming back to here, let me write an equation. Now, see here, if I have constant voltage of 0 volts, will there be any current? No. While changing from 0 to 5, because we need to take time, no, in order to move from 0 to 5, we need to take time. So during that time, you are going to have current. If you maintain 5 volts constant, so my dipole is going to be like this only. Will you expect any current? No, because charge flow should be there for current. Now, if you are moving from 5 to 10, meaning that my voltage, if you are changing the voltage across capacitance from 5 volts to 10 volts, then only current will be there. Now, let me write the equation. IC, capacitance current, is directly proportional to voltage across capacitance or change of voltage across capacitance. Because if you maintain constant voltage, nothing will happen. Okay, voltage across capacitance. That proportionality constant is dVc by dt. C, proportionality constant is called as capacitance. Okay, now this is going to be formula. Now if you see, for DC, if I maintain constant voltage for DC, means can we expect any current to flow through capacitance? No. For AC, currents will be there. Okay, for AC, currents will be there. Now, if you think of design of machine, in the design of machine, in AC machines, capacitance will be there or not? Yes. Of course, we are not going to model because of some other reasons we will discuss in machines class. But anyway, means design of capacitance. Means my capacitances has to be modeled in all AC machines. Differently, we will see in machines. Okay. Now, this is going to be the formula for it. Okay. Next thing is we have to discuss about Coulomb's law. Now, see here. See, means if you see only recombining force, so recombining force, okay, let me think of this is instant 1, instant 2, instant 3, instant 4, instant 5 in time, okay. So see here, if you compare instant 2 to instant 3, okay, at what instant you are going to get more recombining force, at what instant you are going to get more recombining force? People might feel that at second, more recombining force, attraction force, okay? Attraction force between these two, at second instant it will be more, or at third instant it will be more. Some people think that second instant it should be more because distance between the dipole is going to be less here by considering Coulomb's law. Okay, so force of attraction or repulsion directly proportional to Q1 Q2 by d square. Okay, so the moment distance is less, force should be more. The distance is more, force should be less, is wrong. Because the main assumption while saying the Coulomb's law is what? Charges should be point charges. Charges should be point charges, right? So the moment if you want to use Coulomb's law, point charges only, it is valid. Now, what is meant by point charge? If I have, for example, if I have this, okay, if I have this material, if I remove one electron, it is going to be positively charged, it is going to be negatively charged. Now, for this positively charged, spatial occupation is there or not? Yes. For this negative charge also of electron also means space equal, some space it is getting occupied or not. Then what about point charges? Can I say this particular equation is invalid because in our physical system it's impossible to have point charges at all, because in space some occupation will be there for the charge also, because that's a matter. Okay, then why are we applying this? See here, if two charges are there, this is maybe, let us think of this as positive charge, this as negative charge, two charges are there. If the distance between the two charges is so high compared to spatial orientation of these charges, we can assume them as point charges. Okay, for example, maybe our north star, if you see, means if you want me to show north star towards north, I will show with a single finger. Why? Because of course Earth is there and north star can be million times bigger than Earth, complete Earth, but still we are able to represent with a single finger. Why? Because distance is very, very high compared to spatial orientation of either Earth or north star. That's why means we can assume complete Earth as a point and north star as a point. Getting my point, right? So when the distance between the charges is very, very high compared to spatial orientation of the charges, we can assume them as point charges. Now, if you see here, for example, this is positive and this is electron. Now I apply, this is under normal 0 volts condition. Now if I apply voltage here, now what will happen? This electron, this particular electron orbit will be slided towards Earth such that negative will be formed here. Okay, the moment you apply voltage, automatically my orbit of the electron is going to be slided. By what distance? Can it be by meters or millimeters? No. It will be in angstrom units, orbital distance. No. Okay, kind of, if this is positive, and this is going to be orbit, electron. Okay, now means my orbit can be slided like this. Okay, so that slide or distance between the dipoles will be in angstrom units, 10 to the power of -8 meters. Okay, so distance between these will be in angstrom units. Now, can you apply this point charges formula? No, because distance is very, very less. The moment distance is very, very less, you cannot apply this Coulomb's law at all. Rather, dipole moments formula has to be used, and EM theory faculty will deal that. Okay. But anyway, see here, because if you say attraction force here is more compared to here, capacitance will not exist. Right? Capacitance, how can capacitance exist if the distance, if the force here is more and if the force here is less? Because segregation force, if you see segregation force here 5 volts, here 10 volts, so segregation force is increased. Segregation force is increased, and if you think of attraction force is reduced. Attraction force is reduced if you apply Coulomb's law. If you apply Coulomb's law, what would you think? Attraction force from here to here is less. Okay, so recombining force is becoming less and segregating force is becoming more, meaning that that particular rubber band is a kind of aged rubber band, it will break down. Getting a point, right? Now, means the moment segregating force is increased, recombining force also should be increased, then only stable operating point will come. That is nature. That is nature. Now, just by applying your Coulomb's law, you should not conclude, because distance between the dipoles is going to be much less. What is electrical dipole? Two equal and opposite charges displaced by very small distance. Meaning that you are not supposed to apply your Coulomb's law at all, they are saying. Electric dipole does not mean that like two equal and opposite charges displaced by distance. No. Two equal and opposite charges displaced by very small distance is electric dipole. Electric dipole. So Coulomb's law cannot be used here. Okay. Now, next thing is, maybe if I think of this particular formula, okay, let us extend from this formula. If I think of this formula, now VC is going to be how much? 1 by C integral IC dt, right? Now, time limits. Should it be from minus infinite to t or 0 to t? Should it be from minus infinite to t or 0 to t? In order to understand that, we should do some more analysis. Okay. Now, rather than one atom, let me take more dipoles. See here, this is capacitor, and I applied some positive charge here, negative charge here, such that dipoles are there. Many dipoles I am taking. And see here, positive meaning that this is negative and down positive, negative and positive, negative, positive. This is the case. This is the case. Okay. So towards positive side, negative is there. Towards negative side, positive is there. Dipoles are found. For example, you charged this to 10 volts. When did you charge? 10 years back. 10 years back from now, you charged this. Ideal capacitance. Okay, practical capacitor will have leakages and all, but the ideal capacitor. Okay, practical capacitor, if you think of practical capacitor can be modeled in low frequency range, kind of like this. Capacitance and resistance combination, with that combination you can model in low frequency capacitor, low frequency range of practical capacitor. But we are thinking of ideal capacitor now. Ideal capacitor is going to be, you charge it 10 years back. Okay, and now means from past 10 years you did not connect anything to here. After 10 years, now if you connect a voltmeter, how much voltage it should show? Same 10 volts it should show. Because means in order to reduce this particular voltage from 10 to 5, for example, this dipole distance has to be reduced. That's what we discussed, right? It is this. See here, 10 volts dipole distance is more. Distance between the dipole, distance of the dipole. And for 5 volts, it should be less. Okay. So in order to reduce your 10 volts, in order to reduce this particular 10 volts to 5 volts, dipole distance has to be reduced. For example, for 10 volts, this is the case. This is the case for 10 volts. Okay. In order to reduce it to 5 volts, in order to reduce by the time, In order to reduce it to 5 volts, distance between the dipole should be reduced. Now, while moving from black to blue, means then what will happen? This negative is coming down, positive is going up. So, current should be there. Without current, you cannot change voltage in the capacitance at all. Okay. Now, in order to move from 10 volts to 5 volts, compulsorily positive should go up, negative should come down, such that distance of the dipole is going to be reduced. While reducing that, current has to come. But are you allowing current to flow? No. Okay. So, without current, how can you change voltage of the capacitance? How can you change voltage of the capacitance without current? No, it's not possible. So, after 10 years also, if you connect voltmeter, then it has to show 10 volts only. For example, if I connect one resistance, already we know that from here to here you are stretching the rubber band. Meaning that you supplied energy. That is going to be stored energy. Now, if you see here, then what is going to happen? The moment you connect resistance, what is going to happen? Gradually 10 volts now at starting means directly I am connecting these two transients. Okay. As of now 10 volts now, before connecting this particular resistance to this particular capacitance, voltage is going to be 10 volts now. Then what is going to happen? For example, if this resistance is 1 volt, then the moment you connect this resistance, how much current will go? 10 amperes current will go. Now 10 amperes current is flowing through resistance, meaning that it's going to absorb power, it's going to absorb energy. That energy will be supplied by this. How? By reducing distance. Because in order to have current in this direction, positive should go up, negative should come down. Okay? So positive, negative. Positive should go up, negative should come down, such that it will be converted into current. Then, the moment 10 amperes current is flowing, dipole distance is going to be reduced. Meaning that this particular 10 volts is not 10 volts now, because dipole distance is getting reduced. So voltage here will gradually reduce. Sorry. If voltage here is gradually reduced across this, means my current is also will be gradually reduced. That is going to be exponential decay and all. That's a kind of different story. Okay. It means this story is related to transients. Yes. Now, if you think of integration now, what is IC? IC is going to be C dVc by dt. What is VC? Voltage across capacitance. What is IC? Current flowing through that capacitance. Okay. Now, what is VC? Is going to 1 by C integral IC dt. 10 years back, voltage also should be counted or not? Yes. So this is going to be minus infinite to t. Or this can be divided into 1 by C integral minus infinite to 0 IC dt plus 1 by C integral IC dt 0 to t. Because from minus infinite we cannot count, no. So that's why this is going to be initial voltage. They will give you, maybe they may tell you in the question, initially relaxed capacitor. Initially relaxed meaning that till t equal to 0, no charge is accumulated on that, or no energy is submitted to that, such that you can start from here. Or they may tell you, before closing the switch, already capacitor is charged for 10 volts. Under that condition, minus infinite to 0, you are going to take 10 volts. You understand my point, right? Is anything, Coulomb's law is done, the electric breakdown is done, black hole is done. Okay, so that is the thing. In the next session, we are going to deal with inductance and mutual inductance. Thank you guys, and again, kindly subscribe to the channel. And from basics with proper understanding, we are going to go ahead. Okay, thank you guys. Thank you very much.